Welcome back to Calculus 3. I'm Dr. Jeff Groh. Today we're going to talk about Gauss's Divergence Theorem. It goes like this. Suppose R is a region that is bounded by an orientable closed surface denoted by the boundary of R, and has unit exterior normal vector n. If F is a C2 vector field, so it's twice differentiable and the second derivatives are continuous, on an open set containing R and its boundary, then, finally, the integral on the boundary of R of f dot n ds, and this is a surface element, this will be a surface integral, and notice that the left-hand side is equal to the flux of the vector field f, is equal to the integral on all of R of the divergence of f times a volume element dv. Note that this is very similar to the flux version of Green's theorem. However, Gauss's divergence theorem works in R3. Let me point out that the integral on the left is a double integral because it's a surface integral. This is a surface element. The integral on the right is a triple integral because it is a volume integral. In our proof, suppose that the vector field f has coordinate functions m, n, and p. We're going to write this in an unusual way. We're going to decompose this as m00 plus 0 n 0 plus 0 0 p. And then on the left-hand side, we're going to decompose that into a sum of the m00 dot n ds plus the other terms. We'll break it up into three surface integrals. Once we've broken the integrals up, we'll show that the integral of m00 dot n ds is the integral over R of dm dx dv. We'll show that the integral of 0 n 0 dot n ds is the integral of dn dy dv, and so on. We can show each piece separately and then add them together, and that will result in the divergence theorem. We're going to take some generic kidney-shaped blob, and we're going to drill little French fry-shaped blobs all the way through from front to back, like this. If we have the region R, we're going to have these little subregions R sub k. And then we'll assert that integrating around the boundary of R, F dot n ds, that's the flux just on the boundary surface of this big jelly bean shaped object, will be equal to the sum, as k goes from 1 to n, of the surface integral on the boundary of the regions R sub k, F dot n ds. Now this might seem a little implausible because there are a lot of additional surfaces inside of the boundary of R that didn't appear on the integral on the left. But just as with the Green's theorem, there's a cancellation principle. Back in Green's theorem, we had a region in the plane, and we diced this up into small pieces. Adjacent cells would go in the opposite direction. Every time you go around these little cells, you have to go in a counterclockwise fashion. So you go across a particular boundary twice, but in opposite directions. And those path integrals would cancel, leaving only the integrals around the boundary of the entire region. That was a cancellation principle based upon the reversing of the orientation as we went along each of those interior paths. In the present context, there is also a cancellation principle. Suppose we have adjacent little cells here. On adjacent cells, we'll have normal vectors that poke in opposite directions. On the cell on the left, the unit exterior normal has to poke out to the right on the shared boundary. On the cell on the right, the unit exterior normal pokes in exactly the opposite direction. So when we integrate the flux on this shared inner boundary, because of the exact reversal of the unit exterior normals, the surface integrals across all these interior surfaces will cancel out. There's a cancellation principle, and we'll only end up with the integral over the boundary of the entire region not canceling out. We'll have the integral around the boundary of R of m0 dot n ds will be the sum on k, as k goes from 1 to n, of the integral around the boundary of the R sub k's of this m0 dot n ds. And we're going to be slicing this into little French fry shaped parallelograms or parallelepipeds like this, where the slices are going parallel to the x-axis. So we're going to have a back face and a front face. All of the other interior faces are going to cancel out between themselves in this sum. The only ones that will survive are the back face and the front face. Both of those will be x values dependent upon y and z values. The domain of parameters will be y and z because we've cut parallel to the x-axis. We'll have x equals g1 of y and z, and x equals g2 of y and z, describing those two pieces of surface. We're going to have a parameterization, first of all, for the back surface. It's going to be given by g1 of yz, y and z. We'll have tangent vectors ty, and that will be the partial derivative of g1 with respect to y, 1, 0, and tz, which gives us the partial derivative of g1 with respect to z, 0, 1. We need ty cross tz, which gives you 1, and then we put a minus on the middle cofactor, so that's minus the partial derivative of g1 with respect to y, and then on the last part, minus the partial derivative of g1 with respect to z. Now, remember, on these surface integrals, we need the unit exterior normal. And I know that in nds, we can replace that with tu cross tv du dv. The one thing that we need to be careful about is that the order of the cross product will determine whether we have an internal normal or an external normal. You have to examine that to figure out which way it's pointing. In this case, we're on the surface G1, and we have a positive I component to the cross product Ty cross Tz. That's exactly the wrong direction because that will point into our region. If our big peanut-shaped region is like this and our little sliced piece is cut out like this, if the normal on the backside has a positive I component, it's pointing in the wrong direction. We'll have to negate this to put this in the correct order. This gives us the sum as k goes from 1 to n, and we'll break this up into a surface integral on the domain for the region k involving y's and z's for the surface. We're going to have m0, 0 dotted with the vector -1, positive dg1 dy, and then positive dg1 dz, dy dz, plus, that's the integral on the back face involving g1. We'll have the exact same domain of parameters. It's going to be the function m0, 0, the vector field. And in this case, on the front face, it's g2 that's used, and we need a positive I component there. So it's going to be positive 1 and then negative dg2 dy, negative dg2 dz, dy dz. When we evaluate these integrals, we have to evaluate the function m on its respective surfaces. So we'll have the sum as k goes from 1 to n of the integral on this dk domain of m evaluated, we'll do this one first, evaluated on g2 of y, z, y, z. The other parts of the vector dot product will be 0, and we'll have dy dz. To this, we'll have to subtract m evaluated on g1 of yz, z, all times dy dz. This will combine both of these integrals. But I want you to check this out. This is the sum as k goes from 1 to n. Sure, we have the integral on the domain dk, but we can think of this difference as the integral from g1 of yz to g2 of yz of dm dx, all times still dy dz. When you take the integral of this derivative and evaluate it at the endpoints and subtract by the fundamental theorem of calculus, you get this. So check it out. We now have a double integral here over this domain for parameters y and z, and yet we have this additional integral now on the x variable of dm dx. This will be the sum as k goes from 1 to n of the triple integral over the region r sub k of dm dx dv, which is dx dy dz. By the way, similarly, the other components of the vector field F can be equal to the triple integral of their respective partial derivatives, and this completes the proof. Let me give you an example that will be similar to what I'll put both on the exam and on the final exam. Verify the divergence theorem for the vector field F equals x, y squared, z on R, which is the region in the first octant bounded by two x plus 2y plus z equals 6, and the coordinate planes. The region, in other words, is in the first octant, so I'll only draw the first octant. What kind of surface is this? Notice the powers are all 1. It has to be extraordinarily flat. That's a plane. It's a plane with a normal vector 2, 2, 1. But we can draw this very easily. When y and z are 0, x has to be 3. When x and z are 0, y has to be 3. And when x and y are 0, z has to be 6. Connecting these 3 dots, 3 points determine a plane, we have this plane in the first octant. We're also bounded by the coordinate planes, which means the solid that we're dealing with is the tetrahedron cut off there in the first quadrant. It has 4 faces, 1 solid, 4 faces. Whenever I ask you to verify the divergence theorem, you should first write down the equation involved. In the divergence theorem, the flux, evaluated as a surface integral, is the integral over the solid region of the divergence of the vector field F up against a volume element. Since we're up against a volume element, this will be a triple integral. Since this is a surface element, this will be a double integral. It's often easiest to do the right-hand side first. Remember that our vector field was x, y squared, z, and this face was 2x plus 2y plus z equals 6. We'll do the right-hand side first. The divergence of this vector field will be 1 plus 2y plus 1 up against a volume element. Within this region, all of the y values are positive. So we'll be integrating 2 plus 2y and expect a positive contribution from both of these terms. We'll now set up the triple integral using Fubini's theorem. dz, dy, dx. The lower surface is given by z equals 0. The upper surface is given by z equals 6 minus 2x minus 2y. When we project everything down into the xy plane, we end up with a triangle. Goes 3 on the x, 3 on the y. X values will go from 0 to 3. And using vertical cross sections, y values will go from lower curve to upper curve, the lower curve being y equals 0, the upper curve being y equals negative x plus 3. We have a straight line with a slope of negative 1 and an intercept of 3. This is going to be the value of the total flux. With respect to z, the quantity 2 plus 2y is constant. So when we integrate the integral with respect to z, we get the constant 2 plus 2y times the length of the interval. This gives us the integral from 0 to 3, the integral from 0 to negative x plus 3 of the quantity 2 plus 2y times 6 minus 2x minus 2y dy dx. Let's simplify the integrand. We can factor a 2 out of the first bracket and a 2 out of the other bracket as well. Distributing, we'll leave this 3 minus x and multiply that by a 1 plus y. And we'll have minus y times 1 plus y. That's minus y squared dy dx. Let's go ahead and integrate this. We get 4 times the integral from 0 to 3. On the first term, we're going to have 3 minus x times y plus y squared over 2, evaluated from 0 to 3 minus x, minus y squared over 2 minus y cubed over 3, evaluated from 0 to 3 minus x, all times dx. Evaluating, we have 4 times the integral from 0 to 3. Plugging in 3 minus x and distributing, we'll have 3 minus x squared, and then plus 1/2 3 minus x cubed. We get minus 1/2 3 minus x squared minus 1/3 3 minus x cubed, all times dx. Let's combine like terms. One of them minus half of them gives you 1/2 of them. 1/2 minus 1/3 is plus 1/6. If we were to do a u substitution on this integral, we would choose u equals 3 minus x. That means du would be minus dx. And when we integrate it, we would get 1/2 3 minus x cubed over 3 with a minus 1 in front. Same here. We'll have minus 1/6 3 minus x to the 4 over 4. The whole thing evaluated from 0 to 3. When you plug in 3, you get nothing. Plugging in 0, we'll have 3 cubed divided by 3 is 3 squared. That's 9. We'll have negative 9 halves. 3 to the 4th, we can cancel a 3 down here. We'll still have a minus, but it's going to be 3 cubed. That's 27. The 3 canceled here times that, it's going to be over 8. To simplify what remains, we can distribute a negative, and we can also multiply by 8 over 8. We'll distribute this 8 to cancel both fractions inside. We can reduce the other 8, and we'll have 1/2 times 9 times 8. When we distribute, 8 will cancel the 2, leaving 4. 4 times 9 is 36. And then the 8 cancels on the second fraction, leaving 27. 36 and 27 make 63. The total flux is 63 halves. Now this was only the right-hand side. To verify the divergence theorem, we also need to calculate the surface integral on the left-hand side. Let's store this as a value for future reference. On the left-hand side, need to decompose the boundary surface into its four faces. There's going to be surface 1. Around the back we'll have surface 2. On the side, surface 3. And then in the front face, surface 4. The surface being a tetrahedron, it can be decomposed into 4 faces. We'll have the sum over these 4 surfaces. Let's look at surface 1 to begin with. Some of these will be easier to do than others. On surface 1, we can actually see exactly what the unit exterior normal is at each point on that lower surface. It is minus k. It follows then that since f is x y squared z, that f dot n on that face will be minus z. And if we evaluate on surface 1, all the way across surface 1, z is 0. That means that the integral on surface 1, f dot n ds, is 0. There is no flux across that lower surface, surface 1. Let's see if we are as lucky on surface 2. On surface 2, the unit exterior normals will poke exactly in the direction of minus I. It follows then that f dot n will be minus x. And if we're evaluating on surface 2, which is part of the yz plane, we will get 0. So the flux on surface 2 will be 0. What about surface 3? On surface 3, that unit exterior normal is always minus j. That means f dot n will be minus y squared, since the vector field had y squared as its middle coordinate. If we're evaluating y squared on surface 3 is part of the xz plane where y is 0. So we get no flux through the lower face, the back face, or the side face. All of the flux, 63 halves, had better come through that other face, S4. S4 is the plane described by the equation for the plane seen here. So in S4, let's find a parameterization of that plane. We'll solve for z. The parameters will be x and y. Z is equal to 6 minus 2x minus 2y. The tangent vector tx will be 1, 0, minus 2. Ty will be 0, 1, minus 2. Tx cross ty will be 0 minus negative 2. Negative 2, but don't forget the minus on the middle cofactor, making that positive, and then 1. Check it out. 2, 2, 1. That's not a coincidence. So, if we're integrating on S4, f dot n, f, you recall, was x, y squared, z. If we evaluate f on the surface, z has to be 6 minus 2x minus 2y. And so we're going to take f and dot it with this normal, which is pointing in the exterior direction. Because the z component is positive, it has to be going out, up on that surface. We'll end up with 2x plus 2y squared plus 6 minus 2x minus 2y all times dx dy. We just need to set up the limits of integration to integrate over this surface. The domain of parameters for x and y will be over the little triangle, 3 on the x, 3 on the y. X will go from 0 to 3, and y goes from lower curve to upper curve. The lower curve is y equals 0. The upper curve is 3 minus x. We do have a little bit of simplification. We'll have 6 minus 2y plus 2y squared dy dx. That's the integral from 0 to 3 of 6y minus y squared plus 2y cubed over 3 evaluated from 0 to 3 minus x. We have then the integral from 0 to 3 of 6 times 3 minus x minus 3 minus x squared plus 2/3 3 minus x cubed dx. Integrating, we'll have minus 6 3 minus x squared over 2 minus 3 minus x cubed over 3 with an additional minus from the implied use substitution and a minus on the next term. 2/3 3 minus x to the 4th over 4, and we're evaluating from 0 to 3. Plugging in 3, we get 0. So we'll plug in 0. Plugging in 0, we have 3 squared times 3, that's 27, but we have a minus. Plugging in 0, 3 cubed divided by 3, that's plus 9. Then plugging in 0, we get 3 to the 4th divided by 3, that's 3 squared. That's minus 27, but we're still divided by 2. We can distribute the minus. That will give us a minus in the middle only. If we take 27 minus 9, that's going to be 18. We need to convert that to halves. That's going to be 36 halves plus 27 halves, and that is 63 halves. To get the total integral, we have to add 0 plus 0 plus 0 plus 63 halves equals 63 halves, and that gives us the total flux. Since that matched the integral that we obtained by integrating the divergence over the entire region, the solid region, we have verified the divergence theorem in this one case. In our next example, let's suppose that R is described by Z bigger than or equal to 0, and we're capped by Z equals 4 minus x squared minus y squared. So we have a circle of radius 2 in the xy plane capped by an elliptic paraboloid peaking at 4. The solid region inside is the region R. The boundary then will have two faces, the bottom face and the top part as well. Let's verify the divergence theorem, where we'll assume that the vector field F is x squared y and then 3z. Okay, so remember step 1, state the equation involved in the divergence theorem. I'll give you 3 points for that. You take the flux and set it equal to the integral over all of R of the divergence of the vector field up against a volume element. Let's do the right-hand side first because that's usually easier to do. The divergence of this vector field will be 2x plus 1 plus 3 up against a volume element. If you think about the integral of the first term, there will be just as many positive x's as negative x's when we integrate across the solid region. The integral of the first term must be 0. We end up with 4 times the volume. Setting up the limits of integration for this triple integral, you can see that we have 4, and because of the rotational symmetry around the z-axis, we should use cylindrical coordinates. In cylindrical coordinates, the upper surface, z equals 4 minus x squared minus y squared, will be 4 minus r squared. The lower surface, z equals 0, is just z equals 0. When we project down into the xy plane, we get the disk of radius 2. That will have theta going from 0 to 2 pi, and r going from 0 to 2. The volume element will be dz, r, dr, d theta. Note that we get 2 pi for free. We'll integrate the 4r with respect to z. We'll end up with 4r times the length of the interval, which is 4 minus r squared. And that just leaves the integral with respect to r left. This 4 can come out and join the 2 to become an 8. We'll distribute to get 4r minus r cubed for what's left over. That gives us 8 pi times 2r squared minus r to the 4th over 4, evaluated from 0 to 2. Plugging in 2 squared times 2 is 8, minus 2 to the 4th is 16, divided by 4 is 4. The answer is 32 pi. That's the total flux. The boundary surface will have two faces, surface 1 and surface 2. On surface 1, the unit exterior normal is minus k, because it points straight down at each point along that lower surface. That means f dot n will be minus 3z, which if we evaluate on surface 1, z all the way across surface 1 is 0. So the integral on surface 1, f dot n ds, by the way, not that it's relevant, but ds on that lower surface will be dx dy, or r dr d theta, some surface element of the xy plane, because it is a piece of the xy plane. Nonetheless, the flux through the bottom surface will be 0. We need only calculate the flux through the top surface, and for that, we need a surface parameterization. Because of the rotational symmetry around the z-axis, we should use cylindrical coordinates for this surface. That'll give us parameters r and theta. X will be r cosine theta, y will be r sine theta, and z will be 4 minus r squared. The two tangent vectors, tr will be cosine sine minus 2r, and t theta will be minus r sine, r cosine, and then 0. Tr cross t theta will be minus a negative, that's positive 2r squared cosine, minus the product of two negatives and flip the sign on the middle cofactor, that's 4 negatives, that gives us positive 2r squared sine. And then for the last coordinate, we'll have r cosine squared minus a negative, that's plus r sine squared, which simplifies to r because of the Pythagorean identity. Notice that since r is going to go from 0 to 2, r will be positive, which means the z-coordinate of this cross product will be positive, which makes sense because for the exterior normal, we want that z-coordinate to be positive. If the z-coordinate had ended up negative, then the cross product would be in the wrong direction, giving us the interior normal. We would just multiply by a negative to give us the exterior. The next step is to evaluate the vector field on the surface parameterization. So for us, the vector field will be x squared. That's going to be r squared cosine squared, followed by y, which is r sine, and then 3z, that's 3 times the quantity 4 minus r squared. It follows then that the integral on our second surface, f dot n ds, will be the double of the dot product of these two. We'll have 2 r to the 4th cosine cubed theta plus 2 r cubed sine squared theta plus 3r times 4 minus r squared dr d theta, where theta goes from 0 to 2 pi and r goes from 0 to 2. Now we have this cosine cubed, and you might remember that when you cube a cosine, it still has a negative part and a positive part. And those will exactly cancel out. When you cube the positive part, it's still positive. When you cube the negative part, it's still negative, and in exactly the same proportion. Which means that when we integrate cosine cubed, we have to get 0. That doesn't happen for the sine squared. For that, we have to use a half-angle identity. We'll have 2 times r cubed times 1/2 of 1 minus cosine 2 theta. We still have the 3r times the quantity 4 minus r squared dr d theta. The cosine 2 theta, when you integrate from 0 to 2 pi, will of course be 0. We're left with just this r cubed plus these other terms. At this point, we get 2 pi for free. We'll have 12r, a positive r cubed, and a negative 3r cubed is minus 2r cubed. That's 2 pi times 6r squared minus 1/2 r to the 4th, evaluated from 0 to 2. Plugging in 2, 2 squared is 4 times 6 is 24. 2 to the 4th is 16, divided by 2 is 8. 24 minus 8 is 16 times 2 pi gives us 32 pi, same as before. Just as in the plane, we can derive a continuity equation for R3. It goes like this. If you have some region in space, some generic peanut-shaped region in space, the total mass, as you know, is the integral over that region of the density times the volume element. Density will have units of kilograms per cubic meter. The volume element has units of cubic meters. When you multiply them, you get units of kilograms. Added up over the total region, you get the total number of kilograms. That can change, though, with respect to time. You can bring the derivative with respect to time into the integral, but the price you pay is it becomes a partial derivative. And this represents the rate at which mass is going in, the rate of increase. When this is positive, mass is increasing. That's exactly the opposite of flux. If the only way mass can change within the region is by flux across the boundary, then this must be the minus of the flux. But flux, you recall, is the integral around the boundary of f dot n ds. However, by the divergence theorem, this will be minus the integral over r of the divergence of f dv. We can now, the vector field f in this case is rho times v, for the exact same reason as we discussed before. So we'll have the divergence of rho v here. Combining these two integrals, we'll have 0 is the integral on r of the derivative of rho with respect to t plus the divergence of rho v all times the volume element dv. The vanishing of this integral is true regardless of the region R. We don't allow creation or annihilation of matter in any region, and therefore the change in total mass can only happen by flux through the boundary. It follows, because this is true for all r, that if the integrand is continuous, then the integrand must be zero. That's called the vanishing integrals principle. If the integrand were non-zero someplace, by continuity it would have to be non-zero on neighboring points, suppressing the fact that the domain is actually a piece of space. And it follows then as a consequence that zero is d rho dt plus the divergence of rho v. This is called the continuity equation. If you wanted to model something that was not conservative, where you had creation or annihilation, or maybe some additional source, you would add some source term on the other side instead of zero. Keep in mind, this represents conservation of mass. It describes the only way you get changes in total mass is by flux across the boundary, so mass is conserved. Also, we can finagle this equation for various special cases. I want you to consider a process called diffusion. Diffusive processes work as follows. On a microscopic scale, you get absorption and re-emission of some quantity in a random direction. And so this quantity will be jumping at random all over. However, if you have regions with higher concentrations and other regions with lower concentrations, because of the random nature of the walk, these processes tend to be diffused and to spread out in the direction of the negative gradient of density. So rho v in this case will be minus some constant times the gradient of the density. That's true for all diffusive processes. Note that significant examples of diffusion are blue light in the atmosphere. Blue light is absorbed by nitrogen molecules in the atmosphere and then re-emitted, only to be absorbed again by nitrogen molecules and re-emitted in random directions. Because of that, blue light diffuses throughout the atmosphere. When you see blue light coming both from that direction and from that direction, it really is, because it's been absorbed and re-emitted, and it's coming at you then from all directions. In fact, if you have a mountain many miles in the distance, it often has a bluish hue to it. That's because of the blue light from the nitrogen molecules between your eye and the mountain. Blue light is being emitted from the nitrogen molecules between you and the mountain because of this diffusive property. What does the continuity equation tell us about properties that undergo this kind of diffusion? Another diffusive process would be the absorption and re-emission of neutrons in a critical mass. You have neutrons that hit perhaps a uranium atom, splits the uranium atom, and two neutrons come out in random directions, which then get reabsorbed, splitting other nuclei and emitting two more neutrons each, giving a diffusion of the neutrons from regions of high concentration to regions of lower concentrations in the direction of the negative of the gradient. Remember, the gradient points in the direction of maximal increase. The negative gradient points in the direction of maximal decrease, if you will. What does this mean in terms of the continuity? What does diffusion mean in terms of the continuity equation? If you replace the momentum density rho v by minus k times the gradient of rho, you get 0 equals rho t plus the divergence of minus k times the gradient of rho. The minus k can come out of this divergence. And you get the divergence of the gradient of rho. What is this divergence of the gradient? The Laplacian scalar field, which is just a scalar valued function, f, is denoted by triangle f. That does not mean change in f, that's now the Laplacian of f. And defined by the Laplacian of f is the divergence of the gradient of f. What does that look like? The Laplacian of f, we take the del operator, which is dx, dy, dz, and we dot that with the gradient of f, which is fx, fy, fz. What we get is fxx plus fyy plus fzz. Diffusion then implies that the partial derivative of rho with respect to time is equal to a constant k times the Laplacian of density. This equation is called the heat equation. The heat equation is used to model diffusive processes, like the diffusion of heat through a metal plate. Or, for instance, sometimes you need to model the diffusion of heat up a reflex column at a refinery. There are any number of applications to the heat equation. An interesting one was given by Lord Kelvin, who applied the heat equation to the entire planet Earth. He hypothesized that at some point, the whole Earth was a hot, molten blob about 7,000 degrees Kelvin. And slowly over time, heat radiated from the surface into outer space, diffusing from the interior to the exterior. He wanted to know how long it would take for the Earth to cool to its present state, the present state being determined by the gradient of heat as we go down towards the center of the Earth. The surface of the Earth should be much cooler than the interior, because the surface of the Earth is radiating heat outward into outer space and it's cooling. The interior of the Earth, having started out as a hot molten blob, will still have that hot lava inside of it and be diffusing heat outward. In fact, in his day it was well known that as you go deeper and deeper into mines, they become hotter and hotter. Using that estimate of that surface gradient for heat near the surface of the Earth, he was able to use the heat equation to try to determine the age of the Earth. His answers were uniformly bad. He came up with somewhere between 10 million and 400 million years as kind of an upper limit maximum. As an independent method, he estimated that the age of the Sun was maybe 10 million years, based upon a theory that the heat of the Sun is generated by gravitational contraction, just compression. The more you compress a gas, the hotter it gets. Gravity is the force which compresses the gas initially in the Sun anyway, and he didn't know at the time about nuclear fusion, so he thought the only source of heat from the Sun was through gravitational compression of the gases. Using that model, he estimated the Sun to be no more than 10 million years or 20 million years at most. So his two models, the model of heat radiating out from the Earth, giving anywhere between 10 and 400 million years age of the Earth, and the gravitational compression of the Sun, giving about 10 to 20 million years of age for the Earth, were consistent with each other, but both flawed. First of all, with respect to the Earth, he didn't model something very important that accounts for most of the error. A student of his pointed this out. He did not account for convection, only the conduction of heat from the interior through diffusion. He didn't account for the convection currents within the Earth. Accounting for that takes care of most of the error, but there was one other significant source of error, and that was radioactive decay, providing an additional source of heat within the Earth over the course of time. There are so many uranium atoms within the Earth which decay radioactively over time that it significantly increases that age value for the Earth. If you combine both of those, the convection and the radiation providing an additional heat source within the Earth, then the age of the Earth turns out to be more closely aligned with about 4.5 billion years, which is consistent with current estimates. Also, the age of the Sun can be significantly affected by the fact that the heat coming from the Sun is not only through compression, but also through nuclear fusion, something that wasn't known of in his day. In rectangular coordinates, the heat equation will have the form d rho dt is equal to k times d squared rho dx squared plus d squared rho dy squared plus d squared rho dz squared. One of the things that you will study in a course on partial differential equations is how to solve the heat equation. But at least now you know the basis for the construction of this equation, where it came from. The diffusive hypothesis that the momentum density is negatively proportional to the gradient of the density. In our next example, let R be the region bounded by x squared plus y squared equals 4, x plus z equals 6, and the xy plane. I want to find the flux of the vector field F equals x squared plus sine of z, xy plus cosine of z, and then e to the power of y. First of all, let's get an idea of what this region looks like. Looks like we're bounded below by the xy plane and to the sides by a cylinder, radius 2. But then we're cut by a plane. Notice that if x is equal to 2, then z is equal to 4. And if x is equal to minus 2, z will be 8. So the plane will slice across diagonally this way. We're looking at the region in between. We're trying to find the flux. The flux is the integral around the boundary of the region f dot n ds. Now, I don't know about you, but this surface integral looks like it can be broken up into 3 surfaces: bottom surface, side surface, and top surface. That seems like a lot of work. However, we do have the divergence theorem going for us, which says we can integrate a single triple integral over the whole region of the divergence of the vector field times the element of volume. That looks like one triple integral and a lot easier. Let's do the right-hand side. The integral of the divergence will be 2x, derivative of sine z being 0 with respect to x, plus, when we take the derivative of the middle coordinate with respect to y, we end up with x. And when we take the derivative of the last coordinate with respect to z, we get 0. We'll set this up as a triple integral. It's going to be of 3x. Now, when you project down into the xy plane, you end up with a disk. It looks like cylindrical coordinates might be easy to work with. So we'll have dz, r, dr, d theta. X will be r cosine theta. Theta will go from 0 to 2 pi, r from 0 to 2, and the z's will go from the bottom surface to the top surface. The bottom surface is z equals 0. The top surface is z equals 6 minus x, where x is r cosine theta. We don't get 2 pi for free because all of the theta is both in the integrand and in the limits of integration. We're integrating 3r squared cosine theta up against a z. Well, 3r squared cosine theta is constant relative to z. We'll take that constant and multiply it by the length of the interval, which is 6 minus r cosine theta, dr d theta. Distributing, we'll have 18 r squared cosine theta minus 3r cubed cosine squared theta dr d theta. The first term has a factor of cosine theta. If we integrate that from 0 to 2 pi, you got nothing. We need only integrate the last term. First, with respect to r, we'll have 3r to the 4th over 4 with a minus, evaluated from 0 to 2, still times this cosine squared, which is 1/2 1 plus the cosine of 2 theta, using a half angle identity. 2 to the 4th is 16 divided by 4. It's 4 divided by another 2 is 2 times negative 3. Integral of cosine 2 pi is nothing. And so we get minus 12 pi. I want to do one more example because I want to do an example with rectangular coordinates, cylindrical coordinates, and one with spherical coordinates. So let's do an example using spherical coordinates since we've already done an example with the other two. Find the flux of F equals x cubed, y cubed, z cubed through x squared plus y squared plus z squared equals 4, a sphere of radius 2. Find the total flux. According to the divergence theorem, we can just integrate over the entire ball of radius 2 the divergence of the vector field up against a volume element. Let's see. The divergence is going to be 3x squared plus 3y squared plus 3z squared. You can factor the 3 out. X squared plus y squared plus z squared is rho squared in spherical coordinates. Setting up the limits of integration, we have rho squared, but remember the volume element in spherical coordinates is rho squared sine phi d rho d phi d theta. I want you to remember that. Theta for this sphere of radius 2 goes from 0 to 2 pi, phi from 0 to pi, straight up to straight down, and rho from 0 to 2. We do in fact get a 2 pi for free, so that's going to be 6 pi. When we integrate with respect to phi, we're going to get one bump, and that's 2. We're integrating rho to the 4th. That's rho to the 5th over 5, evaluated from 0 to 2. Rho to the 5th is 32, times 2 is 64, times another 2, 128, times 3, that's 360 plus 24, it's 384. How would this have looked if we had not used the divergence theorem, but instead calculated the flux directly using a surface integral? Well, first we'd have to parameterize the sphere of radius 2. That's pretty easy because you just set rho equal to 2 in the conversion formulas between rectangular and spherical coordinates. That'll give us 2 cosine theta sine phi, 2 sine theta sine phi and then 2 cosine phi. Always calculate t phi first. When you calculate t phi cross t theta, you end up with the exterior normal. If you were to calculate t theta cross t phi, you would end up with the interior normal, which is in the wrong direction for the divergence theorem, which is in the wrong direction for flux. T phi is going to be 2 cosine theta cosine phi, 2 sine theta cosine phi, and then on the last coordinate we get minus 2 sine phi. For t theta we get minus 2 sine theta sine phi, positive 2 cosine theta sine phi, and then 0 because there are no thetas in the last coordinate. T phi cross t theta then will be minus a negative, that's 4 cosine theta sine squared phi. Here we get minus the product of two negatives, and we switch the sign on the middle cofactor. That's 4 negatives. That gives us a positive 4 sine theta sine squared phi. And then on the last coordinate, we have a 4 cosine squared plus a 4 sine squared. Sine phi cosine phi, that's 4 sine phi cosine phi. We need next to evaluate the vector field on our surface parameterization. Remember, the coordinates of the vector field were x cubed, comma, y cubed, comma, z cubed. That's going to be 8 cosine cubed theta sine cubed phi, 8 sine cubed theta sine cubed phi, and then 8 cosine cubed phi. We take the dot product of f and t phi cross t theta. Remember, if it's the integral of f dot n ds, it's f dot tu cross tv du dv. So for us, when we take the dot product, we'll end up with 32s all the way across. We'll have cosine to the 4th theta, sine to the 5th phi. Sine to the 4th theta, sine to the 5th phi, and on the last coordinate, it's going to be sine phi cosine to the 4th phi. d phi d theta. Theta goes from 0 to 2 pi, and phi from 0 to pi. Well, we have cosine to the 4th theta plus sine to the 4th theta, which is not 1. In order to calculate these 4th powers, you need to use a half-angle identity. Let's bring this 32 out. We'll have 1 plus cosine 2 theta divided by 2 squared. We'll also have 1 minus cosine 2 theta over 2 squared. All of that times sine to the 5th phi, plus sine phi cosine phi to the 4th, all times d phi d theta. When we square these two, we'll have denominators of 4. We'll have 1 plus 2 cosine 2 theta plus cosine squared 2 theta, and 1 minus 2 cosine 2 theta plus cosine squared 2 theta, all times the sine to the 5th phi plus sine phi cosine to the 4th phi d phi d theta. We get a little bit of cancellation here, and we can combine some like terms. We have this 2. We still have a 2 cosine squared of 2 theta. We need to use the half-angle identity again. We'll have 1/4 times 2 plus 2 times a half times 1 plus cosine 4 theta, all times sine to the fifth phi plus sine phi cosine phi to the fourth d phi d theta. Cosine 4 theta has a period of 2 pi divided by 4, or pi over 2. Since theta is being integrated from 0 to 2 pi, we get quadruply nothing from this term. We end up with just a 3 here, or a 3/4 times that sine to the fifth. There are no more thetas in the integrand, so at this point we get 2 pi for free. Now we can factor a sine phi out of these two terms. We'll have 3/4. We'll convert sine to the fourth to 1 minus cosine squared phi squared. And now we're set up for a u substitution. U equals cosine phi, so that du is minus sine phi d phi. We have the sine phi d phi, we just don't have the negative. Making the substitution, when phi is 0, cosine of 0 will be 1. When phi is pi, cosine of pi is minus 1. We will get this minus. The integrand will be 3/4 times 1 minus u squared squared plus u to the fourth all times du. We just need to multiply things out. We'll also reverse the order of the limits of integration. That gives us 64 pi. If we FOIL this out, it's going to be 3/4 times the quantity 1 minus 2u squared plus u to the fourth. We'll have 3/4 u minus 2u cubed over 3, and then we have 3/4 u to the fourth plus 1/4 u to the fourth. That will be 7/4 u to the fifth over 5, evaluated from -1 to 1, having reversed the order of the limits of integration to get rid of that minus. You can see that the integrand above was even, and we're evaluating from -a to a. You can just as easily evaluate from 0 to a and double it. So we have 128 pi. Plugging in 1, we'll have 3/4 times the quantity 1 minus 2/3 times 1/5. One minus 2/3 is 1/3 times 3/4 is 1/4 plus 7/20. You can see that if we multiply by 20 over 20, we can distribute this 20 and get some simplification. 4 goes into 25 times, and 4 goes into 128 32 times. So far we have 32 pi over 5. 1/4 of 20 is 5. And then 7. 5 and 7 is 12. What is 12 times 32? Well, you get 320 plus 64. That's 384. Our answer is 384 pi divided by 5. Now we've done this integral both ways, both as a volume integral and as a surface integral. Which way would you prefer?